Welcome to the lesson on areas of parallelograms. At the end of this lesson, you will be able to identify figures that are on the same base and between the same parallels. Additionally, you will be able to prove that parallelograms on the same base and between the same parallels are equal in area. You will also be able to prove that parallelograms on the same base that have equal areas lie between the same parallels. Let's look at the figures given here. In the first figure, we have a parallelogram ABCD and a triangle PDC. What is common between these two polygons? First, both the parallelogram and the triangle lie on the same base DC. Second, the vertices A, B and P that are opposite to the base DC lie on the line AP. Line AP is parallel to the base DC. Here these two lines are called parallels. Next, look at the second figure. Here the trapezium ABCD and the parallelogram EFCD are on the same base DC. The vertices A, B, E and F opposite to the base DC lie on the line AF, that is parallel to DC. In both the figures, we have polygons that lie on a common base and vertices that lie on the line opposite to the base. Such figures are said to be on the same base and between the same parallels. Now, look at these figures. Can we say that these figures are on the same base and between the same parallels? No. Though the base is common, the vertices opposite to the base do not lie on the line parallel to the base. Next, we'll discuss parallelograms that are on the same base and between the same parallels. Here are two parallelograms ABCD and EFGH. Let's rearrange these parallelograms. The parallelograms are now on the same base AB and between the same parallels AB and CH. Do you think there is a relation between the areas of these parallelograms? Yes, in fact there is. Let's try to find it. You know that the area of a parallelogram is the product of the base and height. In the figure, the base of both the parallelograms is AB. We'll name it B. Since both parallelograms lie between the same parallels, the height of the parallelograms are equal. We'll name the height H. The bases and heights of both parallelograms are equal. Does it imply that the area of both parallelograms are equal? Yes, it does. Based on this activity, we arrive upon a theorem. Parallelograms on the same base and between the same parallels are equal in area. Now, let's prove this theorem mathematically. In the figure, parallelograms ABCD and ABEF are on the same base, AB, and between the same parallels as AB and CF. We will prove that the area of the parallelogram ABCD is equal to the area of the parallelogram ABEF. When the two parallelograms lie on the same base, two triangles AFD and BEC are formed. In triangles AFD and BEC, AF is equal to BE. This is because AF and BE are the opposite sides of the parallelogram ABEF. Similarly, AD and BC are also equal. These are the opposite sides of the parallelogram ABCD. Now consider the parallelogram ABCD and ABEF. Here AB is equal to CD and AB is equal to EF because they form the opposite sides of the parallelogram ABCD and ABEF. Since AB is equal to CD and AB is equal to EF, we can say that CD is equal to EF. Based on this, we get equation 1. Now, if you look at CD, it is equal to CE plus ED. Similarly, EF is equal to ED plus DF. Based on this, we get equation 2 and 3. On substituting equation 2 and 3 in equation 1, we get equation 4. Cancelling ED from both sides of equation 4, we get CE is equal to DF. In triangle AFD and BEC, we have AF equals BE, AD equals BC, and CE equals DF. Hence, by the SSS congruence rule, triangle AFD and triangle BEC are congruent. As the triangles are congruent, their areas are also equal. Now let's take a look at the complete figure. The area of the parallelogram ABCD is equal to the area of trapezium ABED plus the area of the triangle BEC. Since we just proved that the area of triangle BEC is equal to triangle AFD, we can say that the area of the parallelogram ABCD is equal to the area of the trapezium ABED plus the area of the triangle AFD. This is equal to the area of the parallelogram ABEF. Therefore, we have proved that the area of the parallelogram ABCD is equal to the area of the parallelogram ABEF. Thus, the theorem is proved. Now let's see the corollary to the theorem we just proved. The corollary states that parallelograms on the same base that have equal areas are between the same parallels. ABCD and ABEF are two parallelograms on a common base AB. The areas of these parallelograms are also equal. Let's assume the bases of the parallelograms are B and the heights are h1 and h2 respectively. Applying the formula for area of a parallelogram, we can express equation 1 as follows. Cancelling B that is common in both sides, we get h1 is equal to h2. As the heights of the parallelograms ABCD and ABEF are equal, the common base AB and the opposite side FC are parallel. Thus, the corollary is proved. Remember that all figures that are on the same base and between the same parallels need not have equal areas. Both the figures are on the same base AB and between the same parallels AB and CD. Since ABEF is not a parallelogram, the areas of ABCD and ABEF are not equal. Both these figures are on the same base PQ and between same parallels PQ and SR. Since PQX is a triangle, the area of PQRS is not equal to the area of PQX. Welcome to the lesson on areas of triangles. At the end of this lesson, you will be able to prove that two triangles on the same base and between the same parallels are equal in area. Hello, what do we have here? Two triangles on a common base. What else is common? The vertices opposite to the base lie on a line that is parallel to the base. So, the figure formed has two triangles on the same base and between the same parallels. What can we say about the areas of these two triangles? Is there a relationship between the areas of these two triangles? Recall that the area of a triangle is equal to half the product of its base and the corresponding height. We'll use this formula to see how the areas of two triangles on the same base and between same parallels are related. The triangles ABC and ABD have a common base AB. Let's name it B. The height of triangle ABC is CP with respect to the base AB, and that of triangle ABD is DQ with respect to the base AB. Both the triangles are between the same parallels AB and CD, so their heights are equal. Let's name the height as H. The area of triangle ABC is equal to half the product of AB and CP, and the area of triangle ABD is equal to half the product of AB and DQ. Let's substitute the base and height of both the triangles. The right-hand side of both equations are equal. Therefore, the left-hand side of both equations are also equal. This implies that the area of triangle ABC is equal to the area of triangle ABD. This activity is the result of the theorem: triangles on the same base and between the same parallels are equal in area. Now, let's prove this theorem using the different properties of parallelograms. Two triangles ABC and ABD on the same base AB and between the same parallels AB and CD are given. We will prove that the area of triangle ABC is equal to the area of the triangle ABD. Let's draw BL parallel to AC and BM parallel to AD. The figure ABLC is a parallelogram because the opposite sides are parallel to each other. That is, AC is parallel to BL and AB is parallel to CL. Similarly, ABMD is also a parallelogram because the opposite sides are parallel to each other. That is, AD is parallel to BM and AB is parallel to DM. Parallelograms ABLC and ABMD are on the same base AB and between the same parallels AB and CM. This means that they are equal in area. Let's term this as equation 1. Now, let's consider the diagonals of these parallelograms. BC is the diagonal of parallelogram ABLC. It divides the parallelogram into two triangles ABC and CLB. These triangles have equal areas. Therefore, the area of parallelogram ABLC will be equal to twice the area of triangle ABC. Let's term this as equation 2. Similarly, the diagonal BD divides the parallelogram ABMD into two triangles of equal areas. The area of parallelogram ABMD will be equal to twice the area of triangle ABD. Let's term this as equation 3. Substituting equation 2 and 3 in equation 1, we get equation 4. That is, twice the area of triangle ABC is equal to twice the area of triangle ABD. This implies that the area of triangle ABC is equal to the area of triangle ABD. Thus, the theorem is proved. The converse of this theorem is also true. The converse states that triangles on the same base and having equal areas lie between the same parallels. This implies if the triangle ABC and triangle ABD lie on the same base AB and their areas are equal, then AB is parallel to CD.